So continuing with our quantum mechanics, on this video I just want to look at electron spin. Okay, just to remind you, we're always going to keep coming back to these. Remember we said states were vectors, and this was our notation. We write our vector this way and it's a column of numbers. And we had some other rules for vectors. We said if A is a normalized vector in our space, then if you multiply it by a factor, it's also in that space. So if A wasn't normalized, I'd have to normalize it by multiplying by this factor, and alpha could actually be a complex number. And then our other rule was if A can happen and B can happen, they're both two states of a system, then A and B simultaneously can also happen. And then we defined, we said if A was given by this, we called that the ket, then the dual vector, which we called the bra, we turned it into a row, we made them all complex conjugate. And when you put together the bra ket, the bracket, it's really just the dot product between these two, or overlap between two vectors. Okay, and then we had two quantum rules. We said states of a system are all the normalized complex vectors in that complex vector space, which we called the Hilbert space. And this dot product is the probability amplitude of measuring this state if you're in that state. But that could be complex, and when you multiply it by its complex conjugate, so this is the magnitude squared, is the probability of measuring state A if in state B. Okay. That was our only two rules of quantum mechanics. So on this lecture, I wanted to go over actually what happens if you did an experiment right here with this. And so let's say you go out and you buy some electrons, a whole bunch of electrons. They're pretty cheap. Electrons, a pile of them. They're just regular electrons. There's nothing special about them right here, a whole pile of electrons. Now there's a property of electrons, and that is they have angular momentum. So electrons have angular momentum. Angular momentum. Now if you remember from classical mechanics, the equation for an object is spinning right here. Its angular momentum was I omega, right here. Oh, okay, just as a sidebar right here, remember, this I is really a matrix. They don't tell you that in classical mechanics, and that's really a column vector. So this is really a matrix times a column vector, and this is another column vector. But we're not going to be using that. I was just trying to say that it really pops up all over the place. Okay, but what do we have? We have some sort of, I don't know, let's just say this is the electron and it's spinning right there. And the angular momentum would be off in that direction. Okay, so remember you just use the right-hand rule as you're spinning around. So this would be the angular momentum, and you'd put the I in for a sphere. Okay, so now let's say we have a sensor right here. I'm not going to say how it was made, but it has a sensor right here. It has an arrow on it. Let's say it's pointing this way. Right now we call that up, or the Z, or whatever. And it has a digital display here. Okay, so you get some digital display. And it's got, let's say, some probes coming out. And let's say we bring an electron nearby. And what will this sensor do? It will tell you how much angular momentum is in that direction, in the direction of that arrow. How much of this angular momentum is in that direction? Okay, that's what this sensor does. And it gives you the display right there in the display. Okay, so what does that do? Well, I bring my first electron down, put it by it. What does it measure? Well, it measures 1 or -1. Throw that one in the trash, bring the next one down. Well, actually, better than throw it in the trash, let's put it in a pile. Bring the next one down. What do we get? 1 or minus 1. Bring the next one down. What do we get? 1 or minus 1. All of them. We bring down one at a time. That's all we're going to get is 1 or minus 1. Looks a lot like a coin toss right here, because you're just going to get heads or tails. It's pretty much the same thing right here. This is a two-state system. Just like the computer bit, instead of 0 and 1, we're using 1 and minus 1. Now, when I say, remember, this is just the z component of angular momentum. Now, I should say the units have to work out. The units, you have to have units here. And, well, when I say it's 1 or minus 1, I really mean in units of, the units of that, units of h bar over 2. H bar has units of angular momentum. So this is in units. So this one up here really is saying that when you get here, it's either 1 h bar over 2, and this one it's minus 1 h bar over 2. Now, since we have two states right here, we can designate them by vectors. We can either call them, we could call that in the z direction, right there, or we could get fancy and just call it a little arrow like that. But I think what I'll call is up, U. So we won't use these, we'll use up, right there. That should be a unit vector. That's a state of our system. And for this case, this one, we're just going to be down, right here. So those are the two states of a system, right here, up and down, right here. Okay, so let's just do it for all of these, all of them, and all the ones that we got a +1 we'll put up here. This will be my up pile. This is my up pile. And all the ones that gave me a -1 I'll throw down into this pile. So this would be the down pile. Okay. So once I get done, and I've made an up pile and a down pile, let me go ahead and put these back over here and test them again, right here. If I test these again, I get ups on all of them, which is good, because if they just changed randomly, then this class would be very tough. I need some way of reproducing an experiment. So if I measure this as up, and put it in the up pile, and then measure it again, I should get up again. And same with the down. I should get down again. Once you're in up, you're up. Once you're down, you're in down. Okay, well, let's take this device and let me flip it upside down. If I flip it upside down, then it's going to look something like and here's my leads coming out right here. And then I put my up pile and I put it into here. What will I get if I take all these ups and put them into here? I won't get a 1. I'll get a -1. And what will I get if I put in all the downs? Then I'll get a +1 right here. So it does give me some sort of a directionality to it, because when I turn my device over, I got the opposites. It's not like a thermometer. If you take a thermometer and flip it upside down, you don't get a negative temperature. It has no direction. Temperature is a scalar. But this tells me there's some sort of a vector nature to this. Okay, well, let's bring it back up to where it was. Forget about flipping it upside down. And now, instead of turning it completely upside down, why don't we just turn it 90 degrees? So now I'm going to turn it so it's pointing off in that direction. Here's my digital display and my two little leads coming out right there. And I say, I'll first take my up pile and I'll try each one here. Well, if I take all these electrons, try them all right here, take this one, what do I get? +1 or -1? What do I get on this one? +1 or -1? Do I get +1 or -1? That's all I get, +1 or -1. So I'm either going to get a +1 or a -1. Oops, let me lower that down just a little bit. +1 or -1. Now, if I get a +1, I can't call them an up pile because my arrow is not up anymore. That arrow is off to the right. So maybe I'll call that my right pile. So if I get a +1, we'll call that the right. And if I get a -1, I guess that would be this way, and we'll call that to the left. Well, if I do this, what I'm going to get is I'm going to get half of these. 50% of these are going to be right, 50% are going to be left. So I'm going to get 50% going to the right, coming down here, 50% going to the left. What if I take my down, put it through this right here, through this same thing? I'm also going to get 50% right, 50% left. Okay, that's kind of strange right here. It used to be up, now you seem to be 50% right and left. Well, let's take it back and put it back right. Put it back up. Well, the way it was at the beginning. Right there. Let's take the one of these electrons, we'd label it. Maybe that's one. That's electron 1. We're going to keep track of it. This electron, all of a sudden we came up here, this is still this electron 1. He's now right. But now I'm going to measure this up here. Does he go back to being up? He was up, then he went to right. Then if I move back, does he go back to up? No. This thing's going to go back to 50% up. Well, we'll just say up. 50% down. So, he did not remember, for some reason, when we made the right measurement, we've erased all this information out because when we went back up to the up, he's not necessarily going to be up again. So it looks like every time you make a measurement, you're erasing the past and you're preparing the state. When we measured a right, we prepared 50% of them to right and 50% of them to left. Then when we put it back up here, we prepared that's right to 50% up and 50% down. So every time you make a measurement, you're preparing the state, which means that what we're measuring is not reality. We're always preparing reality every time we make a measurement. Well, what would this one give me? This one would give me 50% up, 50% down. What would this one give me? 50% up, 50% down, 50% up, 50% down. And again, they've lost all their previous history. Well, what if let me see, instead of going, here we had up and down, then we had right and left, then we could turn it like this right here. Can't quite draw it like that, but we'll try. So we've turned it, so this is in and out. So now if we turn this thing in and out, and we take all of these, and we hook it up to all these electrons up here, what are we going to get? Plus or minus 1, plus on every single one. How many of them are going to be in? 50%, we'll call that in, and 50% out. sorry, just O, I guess. Same with this, 50% in, 50% out, 50% in, 50% out, all the way down. Right here. So if I was in any state, any of these right, left, in, out, up, down, and I asked for something outside of it, it would be a 50-50 shot right here. So if I went from right to in, it'd be 50%. Right to out, it'd be 50%, every single one, right here. Well, suppose we have a proposition here that we say this, notice here, I can never know whether the electron is up and right. I can never know you're both of those two because when I measure up, I destroy rightness. When I measure right, I destroy upness. So it's kind of like an uncertainty principle. I cannot know whether this electron is both up and right, or I cannot know whether it's up or in, or and so on, right there. Matter of fact, if we just said, let's say proposition A, the electron is up. Electron is up. And let's say proposition B, the electron is right. Electron is right. Now we ask, what is the probability of A and B? Let's say A or B. A or B. What's the probability that if I grabbed an electron, that it's either up or right? Well, let's say someone gave me an electron that was out of this pile. I didn't know, but let's say they gave me this electron out of this pile. So they're giving me an electron already in the up state. So first of all, if I come along here and say, okay, A is the electron up, and I get, oh yeah, that's true. That's 100%. This A or B would be 100% if they gave me an up electron. This would be 100%. But let's say I turn this around, B or A, for the same electron they gave me. Well, if they gave me an up, and I ask, is it right? I only have a 50-50 shot right here of this thing right here. This would be, I could be a right, or it could be a left right there. Now, it could be a right or a left, the very first measurement I made. And then, once I've made that, now I have to go back and measure whether it's up or down. Well, it's a 50-50 shot on that, so this second one could either be an up or it could be a down. And this one over here could be an up or a left down. So I could get any of these four combinations, but you'll notice right here, this one would say, oh yeah, that's a good one because you had an up. This one you had a right, that's good. This one you had an up, but this one down here, if you got left and down, you would not make it. And so you notice there's 3 out of 4 that you will make it, and only 1 out of 4 you won't. This is a 75% probability. So you'll notice that A or B does not equal B or A. It's not like we had classical logic. Why? Because the act of measuring the first one affects the second one. We never had that in classical mechanics. Things didn't affect other things in the line. Okay, so there is, well, what if we didn't rotate it so much? What if we just rotated it a little bit right here? You know, just, what if it was just rotated, you know, here's my arrow and here's my digitals. We just rotated by some angle theta right there. Well, if we were all ups, let's say they were all ups to begin with, so I took my up pile and put them in here. Now, since I'm only slightly off of up, most of them are going to be +1 right here. The more I rotate this, the more I'm going to get downs and less ups. And the average value of these +1s and -1s, the average value will go as the cosine of theta. You notice when theta is 0, when you're straight up and down, and I put in all my up electrons, they'd all give me +1. And the cosine of 0 is 1. The average value would be 1. Now as I start to tilt this, the cosine drops, and so I'll get less ups and more downs. And when you get all the way to perpendicular like this, then I'm going to get just as many ups as I get down. And, well, whatever, the average value will be 50% +1, 50% -1, and the average value would be 0. And the cosine of 90 degrees is 0. So the average value would go as the cosine right here. We'll figure out how to do all this right here. I'm just getting an overview of it right now. Okay, so now let's come back to just measuring it straight up. The first case right there. So we're just going to come back to our arrow here, our digital display, and our little probes coming out and our electrons, and we got two states right here. We got +1, which we called the up state, and we called -1, which we call the down state. Right here. Okay. Okay. Now, these up and down are actually our orthonormal basis vectors. So up and down are orthonormal. We already know they were normalized, but they're also orthonormal basis vectors. Basis vectors. We'll see later that same with right and left and in out, but right now we're just going to deal with up down. These are orthonormal. What does that mean? That means when I dot this with itself, we already said anytime they're the same, you always get 1. So this is 1. That means they're normalized. Same with down, down. That's 1. But when you do the opposite, different ones, up, down, then you get 0. They're orthogonal to each other, so perpendicular. Just like we did with I and j for our vectors, weren't they? When you dot I with j, you got 0. When you dot I with I, you got 1. So this one is down, up, and that's also equal to 0. So that's when we say they're an orthonormal basis vectors right here. Okay, so now why don't we make up a vector for A and B right here? We know it's a list of two numbers. Now, there's a lot of choices that we can use. Actually, an infinite number of choices we can make for up right here. All we care about is that this squared plus this squared has to equal 1. And it's kind of like in 4a, we could have put our coordinate system, we could have put our coordinates, our x-axis, any way we wanted. When we put our y in there, our y has to be perpendicular to the x. So y could be in any of these places. And then once you fix x and y, then z is automatically fixed right here. So we're on the first one right here, x. X we can make it anything we want, or the up we can make it anything we want. And we might as well pick the easiest. And so this is all going to be by definition right here. We're just going to pick 1 and 0. This is definitely normalized because this squared plus this squared is definitely 1. So this we could call the up basis or the z basis or the, this is just for this up down right here. We're going to call the up vector 1, 0. And we need to make the down perpendicular to this one, so that when we dot them together, we get 0. Well, 0, 1 will work. And let's just check to make sure that these 4 things work out up here. If we dot up with up, remember what we do is to get the bra, we flip it, 1, 0, and do the complex conjugate, but they're real numbers. And then the up, which is 1, 0. If you multiply this thing out, you get 1 plus 0, which is 1. Okay. Now if we do, say, an up and a down, well, this is still 1, 0, and then down is 0, 1. If we multiply this, that's 0 plus 0, which is 0. The other 2 will give me 0, 2, and 1 right here. This will give me 1, that will give me 0, just to show that that's... Okay, so you noticed up is a state and down is a state right here. Well, if up is a state and down is a state, remember right here, if up is a state and down is a state, then up plus down is also a state right here. So that means, so that means up and down is also a state. Let me give it a name here. How about psi? So that's also a state right here. You're both up and down. You can be both up and down at the same time until I make a measurement, and then it's not. But if I haven't made the measurement, you don't know what state. It's kind of like the 2-slit experiment. When I don't see the electron, it goes through both holes. Once I measured the electron, it collapsed it to one of the states. Well, before I make a measurement right here, before I do it, I'm going to be a collection of ups and downs, but that's not normalized because up is just normalized and down is normalized, but up plus down then can't be normalized, so I need to put in, say, alpha 1 and alpha 2 that normalizes it right there. Okay, so now that would be a general state before I made the measurement. Okay, and if I wanted to normalize it, what do? I just make sure that psi is 1. That's what I do to normalize it. The magnitude of itself is 1. Well, let's plug in right here. Remember, what was just the bra of psi? You take the bra of each one and make these the complex conjugate. So it'd be alpha 1 star bra up plus alpha 2 star bra down. Okay, so now let's plug both of these in right here. And so we're left with this, which is alpha 1 star bra up plus alpha 2 star bra down times this guy right here, which is this one up here, alpha 1 up plus alpha 2 down. Okay, I guess I don't need this. Okay, well now we just multiply it through. This times this would be alpha 1 star alpha 1 up, and then multiply these two plus alpha 1 star alpha 2 up, down, plus these two, alpha 2 star alpha 1 down up, plus these two, alpha 2 star alpha 2, down, down. Okay, and now we can use the fact that we know up, up is 1. So that's just 1. All of our dot products are going to be that easy. This one, up, down, 0. Usually always just 0 or 1. Down, up, 0. This one, 1. Oh, okay, so this just gives me, remember what we're doing, we're solving this right here, which we know is 1, is equal to, it looks like it's this, which is just what? Alpha 1, the magnitude squared, plus that last one, which is the alpha 2 magnitude squared. So this, this right here has to be true. It's a normalized, for this vector to be normalized, this magnitude of this squared plus the magnitude of that squared has to equal 1. Now, if we didn't want to do it with the vector symbols and we want to do it with the columns instead, we could have done it like that too. We could have said this vector right there, psi, is equal to alpha 1. Instead of putting the up in there, we could write it as the 1, 0 if we wanted to do it that way instead, plus alpha 2, 0, 1. Okay, and then I can multiply this in. This is alpha 1, 0. Plus, and then this is 0 alpha 2. And then I can actually combine these two together. That's just alpha 1 alpha 2. Well, if I want this to be normalized, that means the magnitude of this squared plus the magnitude of that squared has to equal 1. That's exactly what we said right here. So you can do it either this way or this way. Either way, right here. Either way. Okay. Well, suppose I give you a matter of fact. Let's just do an example right here. Suppose I gave you a psi. Wait, I'm going to actually put in a number for alpha 1. Let's use 1/6 up. So someone gave me this. We'll figure out how to make these right here. And this next one will be, I'll just put the square root of 35 over 6 I in the down. So let's say someone gave me an electron that looks like this. So we'll say they prepared it this way right here. First of all, I just want to first see, is this a normalized vector, psi? Well, what did we say has to be true? That means what has to be true is this times its complex conjugate plus this times its complex conjugate has to equal 1. Well, so what do we get? We get 1/6 times its complex conjugate is still 1/6 plus this square root of 35 over 6 I times its complex conjugate, which is minus square root of 35 over 6I. Okay, that better be 1. Well, what do we get? We get 136 plus I times minus I is 1. 6 times 6, that's 36. Square root of 35 times square root of 35 is 35. Well, this gives me, what, 36 over 36, which is 1. Okay, it is normalized. Okay, that's the first thing. I just wanted to write that it's... Now, the next thing is, write this as a column vector. So, instead of just as vector notation, put it as a column. So this would be 1/6 of 1, 0. This would be plus the square root of 35 over 6I, 0, 1. Okay, now we can multiply those through. So psi is equal to 1/6, 0. This one plus 0, and you get I square root 35 over 6. And then I could add these two together. It's just 1/6 I square root 35 over 6. So I've written psi in terms of its column vector. What is the dual of psi? What is the bra of psi? Well, what do? You turn these into bras of ups and downs, so that's a bra of up, and you take the complex conjugate of that, which is still 1/6. Over here, you take the bra of down, and you put in the complex conjugate. So that would be minus, I guess that would be minus square root of 35 over 6I. Okay, so there would be the bra of it right there. Suppose we asked, you're in this state right here. Now you set up your experiment like this and you ask, what is the probability that you get up? Well, what did we say our rule was? If you're in the state psi and you want to know what the probability of up is, this will give me the probability amplitude, and if I square it, take the magnitude squared, then that gives me the probability. Except we were in the state psi and we want to go to up. We want to know what's the probability of being up. So, first let's get the probability amplitude. The probability amplitude would be psi up. That's what it would be. I could do it with the column matrices, or it's probably easier just with the ups and downs. We already know what this one was. There was my bra for psi, so let's put the bra in right there. So this is 1/6 bra up minus the square root 35 over 6I bra down. Okay, so that's this, and then times up. Okay, and now let's just distribute these through. So this is 1/6 up minus the square root 35 all over 6I down up. Okay, and now from our orthonormality of our state vectors, remember this is just 1 and this one is 0. Remember, all of our dots are either going to be 0 or 1. Okay, so what are we left with? This is gone, so we just get 1/6. Now, that's not the probability. The probability, you have to take the magnitude of this squared. So this would be psi, what I need is psi. Sorry. Actually, this is, if I was in the state U, what's the probability of measuring psi? I actually wanted it backwards. I actually wanted U psi. But what did we say the difference was? The difference is just the complex conjugate, and the complex conjugate of this is still 1/6, so it would be the same answer. And if I wanted to get the probability anyway, the probability, you just find the magnitude of that. So the magnitude of this and the magnitude of that are going to be the same right here. It's just this times its complex conjugate, which is 1/36 right here. So I have a 1/36. So if I had a psi like that and I put my machine like this and measured a whole bunch of electrons, 1 out of every 36 would be up right here. Now we could say, what's the probability of measuring down? Well, we might as well do it the right way. If you're in the state psi, what is the probability of measuring down? like this. We actually want to do that. That's the probability, but we'll first get it without. We'll first calculate the probability amplitude. Well, what do we get? We get down, and then we get our psi, which is just this thing right here. It's 1/6 up plus the square root of 35/6 I down. Okay, and now when we push this thing through, this term's going to be 0. I don't even have to write that out. This is down up, and down down will give me 1. So it's just the square root of 35I all over 6. Okay, and then what do we do to find the probability? We find the magnitude of this squared. So we multiply it by its complex conjugate. So d up squared would be the square root of 35I over 6 times minus the square root of 35I over 6. The i's and the minus i's give me the 1. This would be 35/36. Which makes, so this would be the probability of measuring down. This was the probability of measuring up. And it makes sense because it has to be either up or down. So 35 of 36 of them would be going down, and 1 out of every 36 would be going up. The sum of these two have to equal 1. You notice, when I took the magnitude of this squared, isn't that 1/36? And the magnitude of that squared is 35/36. So when we came back to here, you know, this one right here, up to that right there, this is really the probability of measuring up, and this is the probability of measuring down, right there. That's the only two, and that's what it's always going to be. This is going to be the probability measuring up, and there's the probability measuring down. Everything's going to be kind of similar when we go to rights and lefts. If we wrote it out in terms of rights and lefts, this would be the probability of measuring right, and that'd be the probability of measuring left. So we've know how to handle this. Then we'll start rotating a little bit more and get a little bit more practice in on this. But now you can start to see this is a lot different. It's just vectors, and hopefully the math is pretty simple since most of these dot products are always 0 and 1. Okay.